Justify if the given graph below represents the given polynomial function. Feel free to use any method in proving your answer. Write the answer and solution on the space provided. So we are here to check if the given graph matches with the given polynomial function. So for us to just verify if this graph really belongs to the given polynomial function, the fastest way to do this is by identifying our zeros in the given graph and apply factor theorem using our given polynomial function. So first, let's identify our zeros in the given graph. The zeros are -5, -3, 0, and 3. Having these 4 zeros in the graph, let's apply factor theorem and substitute them in our given polynomial function. So we have here, let's start with the first 0, which is 3. So substitute p of 3 to our polynomial function. This will become 3 squared times 3 plus 5 times 4 times 3 squared minus 36. So by solving this, we have here p of 3 is equal to 9 times 8 times 4 times 9 minus 36. And 4 times 9 is also 36. And 36 minus 36 is equal to 0. So if we multiply 0 by 8 and by 9, we will end up with a 0 result. So therefore, p of 3 is equal to 0, which shows that polynomial function, p of 3 is a polynomial function. Let's move on with our next 0, which is 0. So we have p of 0 is equal to 0 squared times 0 plus 5 times 4 times 0 squared minus 36. At the first glance, we have here 0 squared, and 0 squared is just 0. And multiplying 0 to the rest of the terms, it will end up with a 0 result as well. So therefore, the p of 0 is also equal to 0, which verifies that 0 is really a 0 of our given polynomial function. Let's move on to the third 0, which is -3. So we have p of -3 is equal to -3 squared times -3 plus 5 times 4 times -3 squared minus 36. By solving this, we will have -3 squared is 9. 9 times 4 is 36. And 36 minus 36 is equal to 0. Same process when we multiply 0 to the two remaining factors of the given polynomial equation, it will end up with 0 as well. So we have here p of -3 is also equal to 0, which verifies that p of -3 or -3 is also a 0 of our given function. And finally, the p of -5. When you substitute it to the given function, we will have -5 squared times -5 plus 5 times 4 times -5 squared minus 36. Looking at our given, we will notice, or we will see here that negative 5 plus 5 is equal to 0. And multiplying 0 to the remaining factors of the given polynomial function, we will end up with a 0 result as well. So therefore, p of negative 5 is also equal to 0, which also verifies that it is a 0 of our given polynomial function. So it shows here that the 4 zeros of this given graph is or are zeros of the given polynomial equation. Let's continue verifying. If we will look at the degree of our polynomial function, here we have 2, we have squared, we have a linear term, and we have squared. If we will be multiplying all these terms and adding the exponents, we will have 5. So therefore, this is actually a 5th degree polynomial function, which shows that if there's a 5 degree, it's a 5 degree polynomial function subtracted by 1. This shows the number of turns. So we have here 4 turns in the graph. Let's verify. So we have here the first turn, the second turn, the third turn, and the fourth turn. And also, this is a 5th degree polynomial, and we are only having here 4 zeros. But notice that x squared is or the 0 of x squared is 0, which shows that it is a multiplicity of 2, meaning 0 is used twice as 0 in the given function. And if we have a multiplicity of 2, what happens to the graph is when the graph turns to it, it will just touch the 0 and then turn immediately. Unlike if it's just a regular 1 degree factor without multiplicity, only 1 0, all it has to do is to pass by the given 0. But if it is a multiplicity of 2, it will stop and turn immediately. So having those verifications, we can say that this graph is really the graph of our given polynomial function, which is p of x is equal to p of x plus 5 times the quantity 36. That's it.